Okay, so hi, welcome you all in the week 5 of live interacting session. So, topic is chemical applications of symmetry and group theory. So, what we will be doing this week? So, this week will be briefly discussing about the orthogonalized great orthogonality theorem, and we'll discuss some of the features of the character table of different point groups, and then we'll solve some previous year assignments based on this week's content. Okay, so let me just share my screen and we'll start. Okay, so this week, last week basically we discussed or we learned about how to represent or how to write down the character table of a particular point group, like what are the different features, and we also learned about the irreducible and the reducible representation. How do we actually reduce some of the reducible representation to get an irreducible form? Okay, then the procedure of representing irreducible representation, etc. Should Okay, let me just briefly go through all the topics, then we'll solve some assignments. Okay, so first one is the great orthogonality theorem. Okay, okay, so this is a very important theorem. And what so there are there are several rules associated with this theorem. The basic rule is that, like, first you have to, like, what are the procedures. So first let's consider a molecule, and you have to decide, or you have to think that the point group of that particular molecule. So what is the point group the molecule belongs to? Okay, then associated with the point group there are several symmetry operations, right? let's say uh, let's say water molecule, like H2O. Okay, so what is the structure? OH, H, right? So what is the point group of H2O? Point group is C2P, right? C2P means it has perpendicular C2 axis. Sorry, it has the principal axis of rotation, which is along Z. Let's consider this is Z, and this is X, and this is Y. Okay, so along this principal axis of rotation, along this Z axis, there is a principal axis of rotation C2. Okay, then it has sigma v, like two sigma v's are there, sigma xz and sigma v yz. Okay, so there are four symmetry operations associated with it. So first one is E, which is identity operation. Then second one is C2 along Z axis, that is the principal axis of rotation. Okay, then other two are sigma v xz and sigma v yz. Okay, so then we have to write down the character table, or before writing down the character table we have to first define is there any class? Like class, what is class? Class means the group. So we have a collection of symmetry elements, right? The symmetry operations. Now amongst the symmetry operations, if there are any subgroup of symmetry operations which are in conjugate with each other, that means if we can write down all the symmetry operations in a like a collection of all the symmetric operations by similarity transformation, okay, then we can call that that particular two symmetry operations are in conjugate with each other, okay. Then that subgroup of symmetry operations we call them a class. So before writing down the point character table, we have to first identify if there are any class amongst these symmetry operations, okay. Now for the C2B point group, there are 4 classes. 4 class mean 4 symmetry operations, and each symmetry operations from individual class, okay. So 4 classes means there will be 4 irreducible representation, okay. So number of class will be equal to number of irreducible representation. So the character table will be, so let's say, so this is C2V. Then you have to write down the elements, symmetry elements E, C2Z, sigma V XZ, and sigma V YZ, right? Okay. Now here you have to write the 4 different representations, okay. So there will be 4 class E, C2Z, sigma V XZ, and sigma V YZ, and there will be 4 irreducible representation here, okay. So let's call that gamma 1, gamma 2, gamma 3, and gamma 4, okay. So capital gamma represents some irreducible representation, okay. Now then you have to write down the characters, the individual characters corresponding to that particular symmetry operations, okay. Now how do you define character? Character consists of a basis. Like first you have to identify a basis, and then considering that particular basis you have to operate these certain symmetry operations, and then if the basis changes sign, or if it is symmetric or asymmetric with respect to particular symmetry operation, then you define character, okay. Now the character of the identity element that defines the dimension of the basis, okay. So if the character of an identity element is 1, then your basis is 1 dimensional. That means you choose one basis function, okay. Now if the character of the identity element is 2, then the dimension of your basis is 2, okay. So basically there are 2 basis functions, okay. So character of the identity element defines or represents the dimension of our basis function, okay. Now for this particular C2B point group, the character will be, let's say this is 1 1. So for each point group, for every point group, or for every symmetry group character table, there will be one at least one fully symmetric or totally symmetric representation. That means it will be symmetric with respect to all symmetry operations. That means for one dimensional case it is 1 1 1 1, okay. Then it is 1 minus 1 minus 1 minus 1, okay. Now so these are 4 one-dimensional irreducible representation. Why? Because for the gamma 1 irreducible representation, the character of the identity element is 1, okay. For gamma 2 irreducible representation, the character of the identity element is also 1. So I just said character of the identity element represents the or defines the dimension of the basis function or dimension of the irreducible representation, okay. That means only one basis function is used, okay. Now character, let's say for a general matrix, let's consider for a general matrix, let's say this is 1 0 0 1. So this is a two-dimensional identity representation, and the character will be the trace of the matrix. That means the sum of the diagonal elements. Okay, this is called the trace. So trace of the matrix defines the character of that particular representation. Okay. So if the identity, so that means so for the identity, for the two-dimensional identity matrix, the trace of the matrix will be 2. So that's why if the character of the identity matrix is 2, then that means the dimension of the particular irreducible representation will be 2. Now if the character of the identity matrix is 3, that means the matrix is what? Like this. So this is the identity representation, identity matrix, 3 cos 3 identity matrix, and the character of this identity matrix will be the sum of the diagonal elements, like 1 plus 1 plus 1 equal to 3. So that means if so that your character is 3 means the dimension of that particular irreducible representation will be 3, and dimension of the basis function will be 3. So there will be 3 basis function to represent our symmetry operations. Okay. So these 4 are sorry. Okay, so basically these 4 representation are one-dimensional representation. Okay, that because the character of the character of the identity operations for each irreducible representation is 1. Okay, now we have to we have to write down the name, like represent the irreducible representation. Basically the procedure for nomenclature. Now for rule, there are several rules. So if the dimension of the irreducible representation, or which is equivalent to dimension of the character of the identity operation, is 1, then it will the name of the irreducible representation will start with A or B, right? So if the dimension of the irreducible representation or the character of the identity element is 1, then the name or the Mulliken symbol of the irreducible representation will start with A or B. Okay, and if the dimension is 2, then it will start with E, and if the dimension is 3, then it will start with T. Okay, now there are several subcategories of A and B. Okay, now then we have to look for the proper axis of symmetry, like CN axis. So if the corresponding irreducible representation, the molecule is symmetric with respect to CN, then it will be called A. It will be called A1. Okay, if it is with respect to CN axis. It is A. And if the molecule is asymmetric or antisymmetric with respect to CN, that means if its character is -1, then if it is -1, then the Mulliken symbol will start with B. Okay. Then next we have to look for the any perpendicular C2. Okay. Oh, sorry about that. So then we have to look for any perpendicular C2. So if the molecule is symmetric with respect to a perpendicular C2 axis, then the character, the Mulliken symbol will start with A1. Okay. Or if it is asymmetric with respect to antisymmetric with respect to perpendicular C2, then the symbol will be A2. Okay. And if there are no perpendicular C2 axis is present, then we have to look for sigma H. Okay. Or sorry, sigma V. So if the molecule is symmetric with respect to sigma V, then Mulliken symbol will be A1, and if the molecule is antisymmetric with respect to sigma V, then the Mulliken symbol will be A2. Okay. So symmetric and antisymmetric means character is 1 if it is symmetric, or antisymmetric means character is -1 if it is antisymmetric. Okay. Then next step will be we have to look for sigma H, or horizontal plane of symmetry. So if it is symmetric with respect to sigma H, then the so one so so 1 and 2 basically, A and B basically it is symmetric and antisymmetric with respect to Cn, and 1 and 2 is basically symmetric and antisymmetric with respect to perpendicular C2, or if any perpendicular C2 is absent, then if symmetric and antisymmetric with respect to vertical sigma V. So it can be A1 or A2 or B1 or B2. Okay. Now sigma H comes from prime and double prime. Okay, like A1 prime or A2 prime or B1 prime or B2 prime. Okay, that means if it is symmetric with respect to sigma H, then it will be prime, and if it is antisymmetric or the character is -1 with respect to sigma H, then it will be double prime. Okay. The next step will be I, or center of inversion. Okay, so if it is symmetric with respect to I, then it will be G, or Gerade symmetry, or if it is antisymmetric with respect to I, then it will be U, unGarade symmetry, G or U. Okay, so this way we can define, or we can name our irreducible representation. Okay. So like this, so for this C2P case, so these are called the Mulliken symbol of irreducible representation. So for the C2P case, let's the first representation 1 1 1 1, this is the fully or totally symmetric representation, right? So here character of the identity element is 1, so that means the name will start with A. Okay, then we have to look for principal axis of rotation, which is here C2. So it is character is 1, that means it is symmetry, so symbol will be A. Then sigma, vertical plane of symmetry, xz, first we have to define xz. Okay, then if the character is 1, that means it will be A1. Then next identity element character 1, so that means it will start with either A or B. Then we have to look for the principal axis of rotation, character is 1, so it will start with A. Okay, then we have to go for sigma V, vertical plane of symmetry, the character is -1, that means 2, it will be A2. Okay, then third one, identity element character is 1, then the principal axis of rotation character is -1, that means it will start with B. Okay, then we have to go for vertical plane of symmetry, sigma b here is 1, so that means the representation will be B1. Okay, then the next one will be B2, like this. Okay, then there were 5 different rules corresponding to the great orthogonality theorem. Great orthogonality theorem basically says that the each rows and columns basically you can treat as vector. Okay, so each row and each column can be treated as vector, and each individual vector is orthonormalized. Okay, because they are orthogonal to each other and they are normalized. So orthogonal to each other means if you direct product to irreducible representation, let's say gamma 1 direct product with gamma 2, that means gamma 1 direct product with gamma 2, this is the symbol of direct product. Okay, direct product means character wise, character by character, you are just multiplication. Okay, in group theory it is called the direct product or symmetry product. So if you multiply direct product to individual representation, then the vectors will be orthogonal to each other, that means the multiplication will be 0. Okay, and each individual representation, let's say gamma 1, gamma 2, gamma 3, gamma 4 are normalized, that means each vector is normalized. Okay, and each column is also normalized, and the square of the sum of the character of the identity elements defines the order of the group. Okay, and number of classes will be equal to number of irreducible representation. Like this, there are some 5 important rules. Okay, so here order is 4, like here order is 4. Why? Because 1, this is 4 symmetry operations and 4 different classes, so order is 4. And now the character of the identity operation is square of the sum of the character of the identity operation is also 4. Okay, like this. Okay, now let's solve some of the previous year assignments. Before that, let me just a second. Hello. Yeah. Yeah. Sorry, I can't hear you. Can you just? Mm-hmm. Huh? Yeah. Yes, right now. No, I think the Harini from NPTEL has just joined. Yeah. Yes, sure, no problem. Yeah, I understand that, but I think the joining problem should not be there because some of the students also previously joined. I don't- Yeah, 6 to 8 years. Sure. Yeah, yeah, sure. Okay, so now let me just solve some of the previous year assignments. Okay, the first one is the sum of the squares of the character in any irreducible representation equals to. Okay, so the sum of the squares of the characters in any irreducible representation equals to. Okay, so the sum of the squares of the characters in any irreducible representation equals to. Okay, so there are four different options. First one, dimension of the irreducible representation. Second one is the order of the group. Third one is the number of classes. And fourth one is none of the above. Okay, though the sum of the squares of the characters in any irreducible representation equals to the dimension of the irreducible representation, order of the group, number of classes, and none of the above. Okay, so we just discussed the sum of the squares of the character of irreducible representation will be equal to order of the group. Okay. Second option is the number of irreducible representation the number of irreducible representation of a non-abelian group is equal to number of Number of classes, first option is number of classes. Second option is order of the group. Third option is sum of the characters of all operations. Number 4 is none of the above. Okay, so number of irreducible representation of a non-abelian group is equal to, so we also just discussed today. So like for the C2B point group, there are 4 symmetry operations, right? And 4 symmetry operation represents 4 individual classes. Okay, so number of classes will be equal to number of irreducible representation. Okay, so here number of irreducible representation will be non-abelian group equal to number of classes. This will be the answer. Number 3, consider the point group C2B, how many irreducible representation it will have. Okay, consider the point group C2B, how many irreducible representation it will have. A is 3, B is 2, C is 4, and D is 1. Okay. So point group C2B we also today discussed. So first to answer this question, so then first you have to write down the number of possible symmetry operations. Okay, now for the C2B point group there are 4 possible symmetry operations: E, C2Z, then sigma B xz and sigma B yz. Okay, now then you have to look for if there are any classes. Like classes means if some of the symmetry operations are conjugate to each other, or that means some of the symmetry operations can be written down by similarity transformation. Okay, now for the C2B point group, these 4 symmetry operations form individual classes, like E, C2Z, sigma B xz and sigma B yz form individual classes. Okay, that means there are 4 different classes. So now we have just discussed the number of classes will be equal to number of irreducible representation. So 4 different classes means 4 different individual irreducible representation. Okay, so consider the point group C2B, how many irreducible representation it will have. So C2B point group has 4 classes. So 4 classes means 4 irreducible representation. Okay. Then question number 4. So the tetrahedral point group has 24 symmetry operations. Okay, so the question is, tetrahedral point group, (24) symmetry operations. And 5 classes. Okay. That it has two three-dimensional irreducible representation, and the and basically two three-dimensional irreducible representation. Two three-dimensional irreducible representation. Then we have to find out the number of one-dimensional irreducible representation. Okay, now there are multiple steps here. So tetrahedral point group is given, and the top point tetrahedral point group has 24 symmetry operations. 24 symmetry operations means the order of the group is 24. Okay. Okay, so now 24 symmetry operations means the order of the group is 24. Okay, now there are 5 classes. So 5 classes means what? 5 classes means 5 irreducible representation. Five classes means 5 irreducible representation. Okay, now two three-dimensional irreducible representation are there. It is given. Okay, so 5 classes means 5 irreducible representation, and we know that the sum of the squares of the character of the identity operations for each irreducible representation will be equal to the order of the group, right? So here two three-dimensional irreducible representation are there. So two three-dimensional irreducible representation are there. That means let's say there are 5 irreducible representation: gamma 1, gamma 2, gamma 3, gamma 4, gamma 5. Okay, now two three-dimensional representation are there. That means the character of identity element corresponding to gamma 1, let's say 3, and the character of identity element corresponding to the gamma 2 representation is 3. Okay, two three-dimensional representation are there. Then we have to find out the number of one-dimensional representation. Okay, Now we know that sum of the squares of the character, that means chi e of gamma I squares will be equal to the order of the group H. Okay, so here order of the group is 24. Okay, so then so basically from this, so it will be like 3a square plus 3a square plus chi e corresponding to gamma 3 square plus then chi e corresponding to gamma 4 square plus chi e corresponding to gamma 5 square will be equal to 24, right? Now 9 plus 9 equal to 18 is already gone. Then gamma 3, gamma 4 and gamma 5, the squares of the characters of the identity element should give 6. Okay, no, so if there is one two-dimensional representation, then it will be 3 square plus 3 square plus 2 square plus 2 one-dimensional representation, then it will give 9 plus 9 plus 4 plus 2. So 18 plus 4 equal to 22, 22 plus 2 equal to 24. Okay, that means two three-dimensional representation are already there, that is given. Then if there is only one two-dimensional representation and two one-dimensional representation, then this, according to this formula or according to this rule, the sum of the squares of the character of the identity operations corresponding to each individual irreducible representation will be equal to order of the group is actually satisfies, right? So that means the how many one-dimensional representation will be there. So number of one-dimensional irreducible representation will be equal to 2. Now the question number 5. The D4 point group has order 8 and 5 classes. How many one-dimensional and two-dimensional irreducible representation will be there respectively? Okay, so the D4 point group has order 8 and 5 classes. How many 1D and 2D irreducible representation will be there? Okay, and the answer, so it has order 8, order equal to 8, and number of classes is 5. So number of classes is 5, and D4 it is non-abelian group. That means number of classes would be equal to number of irreducible representation. And we know that the sum of the, so I sum of the squares of the each individual sum of the squares of the characters of the identity operation corresponding to each individual uh, irreducible representation will be equal to the order of the group. Okay, now so now 5 different irreducible representation are there, and order of the group is 8. Okay, so then we have to just uh, we have to just play with the numbers and find it how many 1D and 2D irreducible representation will be there. Okay, so let's just consider one two-dimensional representation will be there. That means 2, then 2 square, then rest are, let's say two two-dimensional representation will be there. So 2 square plus 2 square plus rest is one dimensional. 1 square plus 1 square plus 1 square, then it will be 4 plus 4 will be equal to 8, so it will be greater than 8. Right, so then it will not be possible, this combination will not be possible. Okay, then let's say there is only one two-dimensional representation and 4 one-dimensional representation will be there. Let's say, so 2 square plus 1 square plus 1 square plus 1 square plus 1 square. Okay, and this combination will be equal to 8, which is the order of the group. Okay, so that means this condition actually satisfies the rule. So that means for this D4 point group, to 5 classes means 5 in irreducible representation, 5 irreducible representation, that means 4 one-dimensional irreducible representation and 1 two-dimensional irreducible representation. Okay, so the answer will be 4 1D representation and 1 2D representation. Okay, so this should be the answer. Then question number 6, identify the Mulliken notation for the following irreducible representation. Okay, so there is a character table is given, which is, let's say, this is E, Cn, in C2, I, sigma. This is 1, 1, minus 1, minus 1, minus 1. Okay, so basically for a particular point group, character table is given and one irreducible representation is given, characters of the one irreducible representation is given, and we have to identify the Mulliken symbol. Okay, so answer will be, so to identify the Mulliken symbol, first we have to look for if the corresponding irreducible, whether the corresponding irreducible representation is one dimensional or two dimensional or three dimensional. So here character of the identity element, character of the identity operation is 1. That means the dimension of the basis is 1. That means it is one dimensional irreducible representation. That means the Mulliken symbol will start with either A or B. Okay, now then whether it is A or B, to identify this we have to look for the proper axis of symmetry. So here it is symmetric with respect to proper axis of rotation. That means character is +1. That means it is symmetric with respect to proper axis of rotation. Okay, that's why. So the Mulliken symbol will start with A. Okay, then one or two, identify one or two. We have to go for the any perpendicular C2 axis is present or not. So it is in perpendicular C2 axis is present, and it is antisymmetric with respect to perpendicular C2 axis. Okay, that means the Mulliken symbol will start with A2. Okay, then here inversion symmetry, the character is -1. That means it is antisymmetric with respect to inversion symmetry. Okay, so that means, so the Mulliken symbol will start with A2U. Okay, then sigma, this is sigma h. Okay, now so we have to look for if it is symmetric or antisymmetric with respect to this sigma h. So it is antisymmetric with respect to this sigma, the character is -1. So that's why the Mulliken symbol will start with A2U double prime. Okay, so yeah, so it is A or B. Then CN1 means A, in C2 -1 means A2, I is -1 means A2U, sigma in -1 means A2U double prime. Okay, so the answer will be A2U double prime. So for the next question, a full character table is given, and then we have to identify different irreducible representation or different bases. Okay, so we'll discuss about that. Okay, briefly. Okay, so here a full character table is given where symmetry operations are basically E C2Z sigma V XZ sigma V YZ. Okay, now this is the 4 possible symmetry operations, and we know that it is the C2V point group. Okay, now the characters are also given. Now here this is Mulliken notation. So 4 different class means 4 different irreducible representation. Okay, then this side will be for basis function, like which basis function we are using. Okay, this is for linear rotation and this is for quadratic. Okay, now the characters is also given 1 1 1 1. 1 is fully symmetric or totally symmetric representation, and then the next one is 1 1 minus 1 minus 1 1 minus 1 1 minus 1 1 minus 1 minus 1 1. Okay, now there are several stars are given. This is ry, this is rx, this is xz, this is yz. Okay, then we have to just answer these stars. Okay, just we have to fill these stars. So first question is, what will be the Mulliken representation for this representation? What will be the Mulliken symbol for this representation? Okay, now so character of the identity element is 1. That means the Mulliken symbol will start with either A or B. Then we have to look for the proper axis of proper axis of rotation, and it is character is 1. That means it is symmetric with respect to proper axis of rotation. So the Mulliken symbol will start with A. Then we have to look for sigma xn. So character is -1. That means it is anti-symmetric with respect to vertical plane of symmetry sigma v. That means the Mulliken symbol will start with A2. Okay, so the Mulliken symbol will be A2 here. Then the second question is, what will be this double star? Okay, what is the basis function here? So here linear rotation I will just discuss here. So replace star with correct term. So here a linear rotation means, so rotation along a particular axis. Okay, now let's say this is a two-dimensional plane, and this is x and this is y. Okay, and this is z axis. Okay, now so Rx, Ry, Rz means rotation along that particular axis. So Rz means rotation along the z axis, Rx means rotation along the x axis, Ry means rotation along the y axis. Okay, so here if you consider Rz, okay, that means rotation along the z axis. That means let's say you are rotating clockwise along the z axis. Okay, so now visualize this. So you are rotating clockwise along the z axis. So when you are rotating clockwise along the z axis, then this, so let me just, this is minus y and minus x. So when you are rotating along the z axis, that means this x goes to minus y, then minus y goes to minus x, then x goes to y, and then y goes to x, like this, no? So this is clockwise rotation. Now you have to, so this is one basis rz. Now you have to perform all four symmetry operations with rz, on rz. Okay, now if you first perform identity operation on rz, then the character will be 1, because identity operation means doing nothing. Okay, so clockwise rotation along the z axis, identity operation will be, character will be 1. Okay, then C2Z. C2Z means proper axis of rotation along Z axis. Now this is coinciding with the RZ axis. No, RZ is also RZ also means the rotation along the Z axis, and C2Z also means the proper axis of rotation along the Z axis. Okay, that means the character will not be changed. Okay, this will be 1. Okay, now sigma v xz, sigma v xz, so this is the vertical plane. Sigma v xz means this is x axis, no, this is x, this is z. So imagine this vertical plane containing the z axis. Okay, now let's say, so rz means you are considering, rz means rotating along the z axis clockwise. So let's say this is clockwise direction. Okay, now when you are taking sigma v, that means this plane sigma v, vertical plane, then this clockwise rotation will get mirror imaged to anti-clockwise, like this. No, like your rotation direction was this clockwise. Okay, now when you are taking sigma v xz, then this direction, what will be the mirror image of this direction, like this. Okay, now if it is converted, if it is getting converted into this direction, then this is anti-clockwise. So clockwise direction, clockwise rotation is getting converted to anti-clockwise rotation after you are performing sigma xz operation on rz basis. Okay, that means character will be -1 here. Okay, now again sigma v yz, sigma v yz. Again you are, let's considering, let's say yz means vertical plane containing the z axis and the y axis. Okay, now let's say, so and your rz means rotation along z axis clockwise. Let's see, your direction was this. Okay, clockwise. Now if you are taking yz vertical plane of symmetry, that means this plane yz plane, then this direction will get converted into, like, what will be the mirror image of this direction, like this, right? Okay, so clockwise rotation again it's getting converted into anti-clockwise rotation if you are taking, or if you are performing sigma yz symmetry operation on the rz basis. Okay, and the character will be -1 here. Okay, so the answer, so the double star here, so answer, what will be the answer? So character is 1 1 -1 -1, so same character appears on the rz basis. Okay, so the answer will be rz here. Then question number 3, replace star star star. means we have to replace this. Okay, so this is the quadratic one, that means binary product of like basis function, okay, or Cartesian coordinates, binary products. Now, so okay, so we have to replace this, and we know all the characters. After performing this basis function, we know all the characters: 1 1 minus 1 minus 1. Then we have to just replace this. So basically, if you imagine dxy function, this is again, let's say, x y minus y minus x, and this is z. Okay, now if you imagine dxy, so this is dxy, right? If it is in two dimensional, if it is x, it is y, then dxy will be like this. Okay, dxy will be like this. Now you are performing all four symmetry operation. So character, if identity element, the character of the identity element will be 1, because identity operation means doing nothing. Okay, then you are performing c2 z. c2 means 180 degree rotation along the z axis. Now along the z axis, that means z axis is above the plane here. Now along the z axis, if you are performing, or if you are rotating clockwise 180 degree, that means this minus this sign will be, so this is plus plus plus, and this is plus minus minus, this is minus plus minus, and this is minus minus plus. So if you are performing 180 degree rotation, okay, then this plus will come here, and this minus also will come here. Okay, so this will generate indistinguishable conformation, that means character will be 1 here. Then sigma v xz. Sigma v xz means vertical plane containing x-axis and z-axis. So z-axis is above the plane, so that means let's consider mirror is here. Okay, like this, mirror is here. Okay, now the mirror is, if it is here, then this plus will get mirror imaged into here plus, then minus will be here, but it will not generate indistinguishable conformation here. So character will be minus 1, right? And sigma v yz also, the character will be minus 1. Okay, so that's why the binary product of x y combination will act as a basis for this representation. It is also easy if you just do the x and y individually, and then just multiply this. Okay, so identity element E will be, character will be 1, then c2z. c2z means performing clockwise rotation along z axis, 180 degree rotation along the z axis, right? So x will become minus x, y will become minus y, and if you just multiply minus x minus y, then it will be xy. So it will generate indistinguishable conformation. Okay, so character will be 1 here. It is symmetry. Then sigma v xz. Sigma v means vertical plane of symmetry containing x-axis and z-axis. Okay, now so x-axis and z-axis, so while y will get converted to minus y and x doesn't change. Okay, so minus y times x, it will be minus xy, so character will be minus 1. And sigma b yz means vertical plane of symmetry containing y-axis and z-axis, so x will get converted to minus x, so minus x times y will be minus xy, so character will be minus 1 here. Okay, so easily you can see that this irreducible representation will be corresponding to the xy basis. Okay, so easily you can another way was, so performing symmetry operations on x y individually. Okay, so e will be 1, c2 z will be equal to, so c2 for the c2 z, what, x2 minus x, and y2 minus y, so it will be minus x times minus y will be xy. Okay, so xy to xy, so character of c2z will be equal to 1. Then sigma v xz, sigma v xz, sigma v xz to x to x and y to minus y. Okay, that means xy to minus xy, so the character of sigma v xz will be equal to minus 1. Again sigma v yz, x2 minus x, y2 y, so xy to minus xy. Okay, so the character of sigma v yz will be equal to minus 1. Okay, so xy binary product can act as a basis function for this particular irreducible representation. Okay, now the next question is, what will be this place? This place means here linear rotation. Okay, linear rotation means here rx, ry, rz can act as a basis, or x, y, z can act as a basis. Okay, now here already this is rz, okay, and this is xy, this is a2. Okay, then we have to find this. Okay, now this is identity element character 1. This is totally symmetric representation. Identity element character 1, c2z character 1, sigma b xz character 1, sigma b yz character 1. Okay, now for the linear rotation means rx, ry, rz can act as a basis, or x, y, z can act as a basis. Okay, x, y, z means linear there. So identity operation, if you take z, so identity operation character will be 1, c2z means rotation along the z axis, character will be 1, sigma b xz vertical plane containing x and z axis, character will be 1, sigma b yz, that means vertical plane of symmetry containing y and z axis, character will be again 1. So here easily you can see the linear rotation, here z can act as a basis. Okay, so here the answer will be z. Okay, so the other assignments are basically repetitive quite, and the next so we have some applications related to the symmetry of the molecule and the quantum mechanics. So what is the relationship between the symmetry and the quantum mechanics? Okay, now we are just here today also we are talking about the different basis functions. Okay, so there are many basis functions you can use to write down the character table. So you can perform the symmetry operations on the chosen basis and you can write down the character table. Okay, so dependent upon the basis function it can be irreducible representation or reducible representation. Okay, now for the quantum mechanics you can so you learn that in the time independent quantum mechanics you learn that h psi equal to e psi, right, where h is the Hamiltonian, psi is the eigenfunction, and e is the eigenvalue. So this is the eigenvalue equation. So h is the Hamiltonian operator. So if you are performing an Hamiltonian operator on an eigenfunction psi, then you are getting the same function back psi with the constant term with energy eigenvalue. With e is the energy and you are getting back same eigenfunction psi. Okay, so this is time independent Schrodinger equation, you know that. Now the eigenfunction of this time independent Schrodinger equation, so let's say h has 2 cos 2 matrix, h is 2 cos 2 matrix, that means it has two states or two energies, that means it will have two eigenfunctions. Okay, so each eigenfunction can act as a basis. Okay, for irreducible representation. So each eigenfunction can act as a basis for irreducible representation. Okay, so the main message is that psi I, that means eigenfunctions of a Hamiltonian operator can act as basis for irreducible representation. Okay, now when you are in quantum mechanics, when you are getting energy eigenvalue or energy value like average energy E, what you do, you basically integrate psi star h psi like this d tau divided by psi star psi d tau. Okay, so you use this kind of formula. Okay, when you compute the average energy. Now so you are doing this integrations, psi star h psi star is the complex conjugate of eigenfunction, h is the Hamiltonian operator, and psi is the eigenfunction, and d tau is the volume element. Okay, now the integration, this type of integration psi star h psi d tau in symmetry or group theory, it will be a direct product. So because why? Because I just said ki psi can act as an eigenfunction, psi is the eigenfunction here, so eigenfunction of a Hamiltonian operator can act as a basis for irreducible representation, right? That means so this will be a basis for a irreducible representation, this will be basis for irreducible representation. Okay, that means this type of integration will be a direct product. Okay, a direct product means symmetry product of a particular point group. So consider a molecule, and for that particular molecule there are many eigenfunctions, and each eigenfunction can act as a basis for irreducible representation, or combination of eigenfunction can act as a basis for irreducible representation, and the integration of wave function means the direct product between two irreducible representation. Okay, and the direct product direct product we represent, let's say gamma 1 is one irreducible representation, direct product and gamma 2 is another irreducible representation. Okay, and this is called the direct product. The symbol looks like this. Okay, that means character wise multiplication. So if you know the point group or character type point group, then you know the character table corresponding to that point group, and if you just multiply character wise to individual representation, then that will be direct product. Okay, now the integration will exist, this type of integration will exist mean non-zero. Integration means area, no? So if integration exists means if integration value is non-zero, then the direct product of two or three irreducible representation must have a totally symmetric representation, like AG or A1, like this. Okay, that makes sense. Because why? Because integration means you are just summing it up. Integration means area of like integration means the area, so you are just sum of all the you are just summing all the contributions. So just for visually understand this, so let's say this is a sine function, and if you integrate up to this, then this is positive part and this is negative part, right? Now this positive part and this negative part will get cancel out each other, and the integration will be 0, right? Like this. If integration so to have this integration value non-zero, or to exist this integration, the direct product has to have some totally symmetric representation. Why? Because totally symmetric representation means character corresponding to all the symmetry operations will be 1. That means it will be symmetric with respect to all symmetry operations. Okay, so then the characters or the direct, when you are multiplying two individual representation, then the character won't cancel out each other, like positive or negative will not cancel. Okay, that's why the two direct product of two or more individual representation has to have one totally symmetric representation to have this non-zero integration value. Okay, so this is related with the transition moment integral in spectroscopy. Like when you are in spectroscopy, when you are computing the oscillator strength, like what is the intensity of the spectrum, then what you will do, so spectroscopy means the transition from one energy state to another energy state, right? By laser or by anything, you are just transition from one energy state to another energy state. So let's say your initial state is psi I and your final state is psi f. Now these two states are connected by the dipole moment, let's say. Now the transition moment integral in short form TMI be related to this psi f mu psi I mod square. Okay, this is transition moment integral, a mod square will be intensity. Okay, now this psi has certain symmetry. This psi as a basis function of some irreducible representation. Okay, let's say this is gamma 1, and mu has certain symmetry, let's say it is gamma 2, or psi I, it has certain symmetry, or certain it acts as a basis for some irreducible representation, let's say gamma 3. Okay, so this integration means direct product of gamma 1, gamma 2 and gamma 3. Okay, now this, if this integral exists or it has non-zero, if it has non-zero value, then you can observe the peak, like peak intensity will have non-zero value. So to have non-zero value of this integral, the direct product of these three irreducible representation must have some one totally symmetric representation, at least one totally symmetric representation. Okay, like this. So we'll discuss this in the next week in detail, and we'll solve some problems or assignments related to this. Okay, so symmetry has direct consequences in quantum mechanics, and in many quantum mechanical problems can be directly solved or can be easily solved by using the symmetry or the direct product basically. So direct product will be useful in molecular orbital theory, in inorganic chemistry, in quantum mechanics, and in many fields. Okay, it will be useful. Okay, so we'll discuss that in detail in the next week. And yeah, so thanks for joining. See you in the next